This next example is a problem from the textbook, number 4 from section 1.5, and it's given y prime is equal to t minus y divided by t plus y, and there's the initial condition y of 0 is equal to negative 1. And so for this example, we want to ask, is there a solution to this? All right, we don't actually care exactly what that solution is, but we want to know, does one exist, and is it unique? Right? And so looking at Picard's theorem, the first thing that we're going to ask is, well, what about that function, right, which is equal to y prime, so just a t minus y over t plus y. Is this continuous at our point, and on what rectangle would it be continuous? And for this one, you could just start out and notice, as long as t is not equal to negative y, or y is not equal to negative t, right? So if t was 2 and y was negative 2, you'd have a 0 down below. As long as you don't get a 0 in the denominator, you're good. This is continuous. So as long as there's no 0 in the denominator, Picard's theorem guarantees that there is a solution. Whether it's unique, we don't quite have enough information yet. And so looking at this particular problem, we have 0 for t and negative 1 for y. And sure, those are different, absolutely. And so there will be a unique solution for some rectangle, some region around our point. Again, Picard's theorem directly doesn't say exactly what it is, but as long as that rectangle doesn't include a discontinuity, you'll be okay. So in this case, we're just avoiding where t is equal to negative y. Or in other words, in your picture, right, I just drew the slope field. Along this direction of, or this line, y equals negative t, we see that the slopes are approaching the vertical, and so in fact you have these undefined slopes along here. And so what this is saying is, as long as we're not touching this section, we'll be okay. Or at least there will be a solution. Now, what about uniqueness? What about unique solution? So in order to see if it's unique, we need to take a derivative with respect to y. Oh, and excuse me, I should have mentioned that this is a function of t and y. Great. So the derivative with respect to y here, if you work it through, let's see, you would get right here, you'd have 1 over t plus y, and then have a negative, and then you'd have that minus t minus y. You could also use the quotient formula if you want. For some reason, I just always like to do it as a product rule. All right, anyway, the biggest thing that we're looking for, we don't actually care too much about the specifics of this derivative, except that we still have t plus y down below. So this one also says, well, where is this continuous? Well, as long as t and y are not equal of opposite signs. So as long as this doesn't happen, we have a unique solution, right? So the first equation says, as long as this doesn't happen, we have a solution. This equation says it will be unique as long as this is continuous. So what does that mean? So for our particular function, yeah, if we plug in y being negative 1 when t is 0, so that's sort of about right here. Oops, I'm drawing in white. That's not helpful to see. About right there. So if I drop the leaf right there, it will sort of have a nice direction that's going to flow in. If I try to start a leaf along a vertical, or like, where does it go? Does it go up? Does it go down? Don't even know. Right? It's undefined there. And so as long as our point, wherever you want to pick one for your initial value, as long as it's not on that place where the function and the derivative are undefined, as long as that doesn't happen, you will have a unique solution. So in this example, if you start it up here, it looks, just sort of to eyeball it, it looks like it would swoop down a little bit, maybe swoop over, maybe start swooping up, I don't know, something like that. All right, great.